A good day to every learner out there today. I am Joseph Eyitayo Olubusade. You are welcome to the Center for Open Distance and E-Learning of the Federal University of Technology, Minna, Niger State, Nigeria. I'll be taking you on the course General Physics 2. I hereby implore you to pay maximum attention as we begin. Thank you. In this course, titled General Physics 2, we shall discuss about the Module 1, which is elastic property. Unit 1 under the Module 1, we shall be discussing about elastic property of materials. And under the Unit 2, we shall be discussing about moduli of elasticity. Module 1, Unit 1. In this unit, materials will be considered as either elastic or non-elastic. It is good to note that some materials possess certain properties which would enable them to return to their original dimension after the removal of an external force, which might have caused a compression or an expansion. This property is known as elasticity. Some other materials do not possess these properties, but are the application of an external force. This material will attain a new dimension which is totally different from the initial or original dimension. On the other hand, some materials will neither retain their original dimension nor attain a new dimension. Rather, they would break at the application of the external force. For instance, let us consider the following materials. If you consider these materials very well, we will realize that these various materials would behave differently when external forces are applied on them. Some, after compression or expansion, will return to their original dimension. Some others will keep extending, behaving like plastic, whilst some would break at the point of application of the external force. Therefore, materials that will regain their original dimension after being deformed are known as elastic materials, while materials that will not regain their original dimension are known as non-elastic materials. Self-assessed exercise. Let's consider the 7 different materials presented in Figure 1. Let's try and classify them into either elastic or non-elastic materials. It is also good to note that different matter components behave differently to elasticity. For instance, if we are to consider fluids, which include liquid and gas, we will realize that they can be compressed and they can also expand. But when considering solids, we know they can also expand, but their compression is somehow difficult because of their rigidity. And so, it is noteworthy that fluids resist the change of volume and not shape, because they don't have a definite shape. So they possess volume elasticity. On the other hand, solids will resist change of both volume and shape because of their rigidity. So they are said to have possessed volume elasticity and shear elasticity. Now, let's go into the definition of common terms as they apply to elastic property of materials. Elasticity. This describes the ability of a substance to regain its original dimension after being distorted. Elastic material. This is a material that will regain its original dimension after being distorted. Elastic limit. This is the limit of force beyond which a deformed elastic material loses its original dimension after the removal of the external force. This is to say that if the applied force is beyond the elastic limit of the material will no longer behave as an elastic material or a perfect elastic material. Yield point. Yield point is that point beyond the elastic limit in which the elastic material has yielded all its elasticity permanently and has become plastic. This is to tell us that at yield point, an elastic material must have lost its elasticity completely and is now behaving like a plastic. This is to say that at the application of any force, the material will keep expanding without regaining its original dimension. Ductile material. A ductile material is that material that is undergoing plastic deformation and will lengthen until it finally breaks. A ductile material is a material that has lost its elastic property completely and is at the yield point whereby it is behaving like a plastic. A brittle material is a material that will break after the elastic limit is reached. That means a brittle material has no yield point, and so immediately after the elastic limit is reached, such material will break off. In order to quantify the relationship between force and extension of an elastic material, Hooke has proposed a law for elasticity, which states that the extension experienced by an elastic material is directly proportional to the applied force, provided that the elastic limit of the material is not exceeded. Mathematically, this can be written as F is directly proportional to X. And if our constant of proportionality K is brought in, then we have F is equals to Kx. F is measured in Newton. X is measured in meters. And K is measured in Newton per meter. K is known as the elastic constant of the material or the stiffness of material. Hooke's law can better be explained using the image or object in figure 2. As we can see in figure 2, L0 is the original length of the spring when it has not undergone any deformation. If we look at the B part of the image, we will realize that the attachment of a mass M has caused a deformation in the spring, which has already led to an increase in its length. And to calculate that increase, we call it extension. Our extension x is equals to the difference between the new length and the original length. According to Hooke's, force is equals to constant times the extension. Hooke's law can also be explained in figure 3. From figure 3, we could see the image of 3 different springs. The image A represents that of a spring when it has not undergone any deformation. The B part shows the action of M1 on the spring, which would undergo a deformation of X1. The C part of the figure shows the action of mass M2 on the spring, which will undergo a deformation of X2. If we compare the two together, we will realize that mass M2 is larger than mass M1, and so we expect the deformation in C part, that means the action of mass M2, to be greater than the deformation of the spring in when mass M1 was considered. Still, F is equals to Kx, and if K is made our constant of proportionality, we could write that K is equals to F over X. Still on the same note, if our elastic constant, that means our elastic limit, is not exceeded, then K can become a common constant, and so the fraction F1 over X1 is also equals to F2 over X2. And so if K is regarded throughout the experiment as constant, we could have F1 over X1 is equals to F2 over S2. Hence, F1 X2 is equals to F2 X1. From the simple illustration in figure 3, we could simply conclude that the deformation experienced by any elastic spring is directly proportional to the applied force, and that the greater the force, the greater the deformation. The graphical representation of Hooke's law is presented in figure 4. Figure 4 is the graphical relationship between force and the deformation in an elastic material. As we could see from the graph, between point O and point A, that means the point whereby the material still retains its elastic property, any little addition in force will result in corresponding increase in deformation. That means force is directly proportional to extension. Between point A to point C marks the yield point. This is the point whereby the elastic limit of the material has been exceeded. Now the material no longer behaves as a perfectly elastic material. Between point C and D, at this point, it is expected that the material must have yielded all its elasticity. That means it will no longer behave as an elastic material, and at this point the material now behaves like a plastic. Behaving like a plastic means that any little addition in force will result in an abnormal increase in deformation, and the material will no longer regain its original dimension. Between point D and point E marks the breaking or fracture point of the material. That means at this point, any further increase in the force will result in fracture or a final break off of the material. For example, if a force of 50 newtons stretches an elastic spring by 40 centimeters, what would be the elastic constant of the spring? By itemizing the given parameters, F is equals to 50 Newton. X is given as 40 centimeters. To convert this to meters, we simply divide 40 by 100, which will give us 0.4 meter. And K, the constant, is the unknown factor that we are looking for. From Hooke's law, we know that F is equals to Kx. By simple substitution, we will obtain that 50 is equals to 0.4 K. Making K subject of the formula, we will have that K is equals to 50 divided by 0.4, and the answer would be 125 Newton per meter. Let's consider a second example in which an elastic wire extends by 3.0 centimeters when a mass of 50 grams hangs from it. What magnitude of mass would cause an extension of 5.0 centimeters, taking G as 10 meters per second square? Now, by itemizing the given parameters, we could see the following, in which K is unknown and M2, which is what we are looking for, is unknown. By considering all this, we could first compute our K from M1 X1, and the corresponding value of K would be used with X2 to get M2. On the other hand, if we recall that F is equals to mg, which is also equals to Kx, we could come out with this relation, and by further expanding the relationship, we could see this relationship coming out. By simple substitution, we could obtain this, and by simple computation, we could obtain this, in which 2500 is equals to M2 by 30, making M2 our subject of relation. We have that M2 is equals to 2500 divided by 30, and by simple mathematics, this will give us 83.33 grams. For the Module 1 Unit 1 of this course, 2 exercises have been given to you, and you are expected to respond promptly and rightly to the exercises through the right channels. Module 1 Unit 2.